Okay, great. So yeah, thanks for the intro. So yeah, indeed, I'm a student in Michael Hoyser Laboratory in University College London, and I've been working with NeuroPixels probes for 3 years now, most of the time combining them with optogenetics. So these recordings aren't really different from regular NeuroPixels recordings that you have heard about over the past few days, but they have a few specificities which I think are important to keep in mind when you're analyzing your data, if you want to properly be able to interpret it. So in particular, due to the fact that, as Andy mentioned, you trigger light-induced artifacts on your probes when you shine light on your brain. So we're going to go through these things. So first of all, here's our setting. You just delicately inserted a brand new NeuroPixels probe in the brain, and you fire up SpikeGLX or OpenEFEs, depending on which software you want to use, and you get some data. And you're very happy. You see beautiful spikes, which are spanning several channels due to the high density of the NeuroPixels probe. And you very quickly realize one of the great frustrations of electrophysiologists, especially when working in an imaging lab, which is that you are blind. You do not actually see your neurons. You do not have any information about the morphology or the genotype of the cells you're recording. This cell here might very well be a big projection neuron in your system or a local interneuron. There is no way to know like that, but there are ways around it. One thing you can do is look at features related to the neurons that you record from. A first source of features is the shape of the waveform of your neurons, which might be large or narrow depending on your cell type. And you can also look at the timing of the spiking of your neuron of interest. Then you can plot your neurons in this feature space that you just defined. And here's an example from a paper from the Poulet lab from 2 years ago, where they plot the peak-to-through ratio against the width of the waveform of all the neurons they record in motor cortex. And you end up, in general, with a big blob like that. You can try to find clouds which are independent from each other. You can try to run different clustering pipelines in this feature space, but really, clustering is an art, and it's really dependent on the set of features that the experimentalists will decide upon. What you want to be able to make convincing arguments is some ground truth data. You want to be able to tell that this neuron up there in the corner corresponds to a big projection neuron or a local interneuron. And one of the most widespread ways to obtain ground truth data in modern neuroscience is to use optogenetics. You can express specifically channel rhodopsin in your neuron of interest, here a local interneuron, and then so first shine light on the brain in the first part of the recording, and later study their physiological activity and plot them in this feature space and look where they fall on these clouds. And the authors of this paper, for instance, decided to draw a line there, which is a debate for another day, and call all these neurons probably positive interneurons. This strategy, this concept of harnessing optogenetics, not to directly manipulate the activity of neurons to study their function, but rather to first identify them in the first part of the recording before studying their activity under physiological conditions, is coming from the Zato lab about 10 years ago. And this is described in details in this paper if you want to read about it. And this is only one of the ways you can use optogenetics. This is something we do in the lab, but of course, you can use optogenetics for many other reasons. As soon as you want to go beyond correlational evidence and you want to causally perturb your system, you will have to make your neurons fire in a way. And also when you do imaging, you also shine light on the brain and you will have to deal with artifacts. So now I'm going to stop talking about science, and on the next 30 minutes, I'm going to focus on the technicalities of how to deal with NeuroPixel recordings with light artifacts. So we're going to first talk about the data acquisition. What kind of devices can you use to deliver light on the brain, before talking about spike sorting and data processing. As you've learned in the past few days, in Marius and Nick's tutorials yesterday, you can use kilosort and phi to automatically cluster and then manually curate your data using the temporal shape and the spatial spread, really the spatial temporal footprint of your neuron, to end up with this data format, which is a time series for each neuron against neurons, where each of these spikes is associated with a given waveform chip. This is what you deal with. And once you have so we're going to talk about spike sorting in a context where you have artifacts, even though Andy already talked a bit about it. Once you have very clean neurons, you want to be able to tell whether they respond or not to light. And this will be the last part of the talk. I'm going to briefly mention how you can tell that a neuron responds to light or not, and tricks you can use to address this question. Okay, let's start with data acquisition. So this is the setting we've been using in the lab over the past few years. A simple LED positioned above the brain surface. Here in the bottom right, you can see the tip of a typical Thorlab LED tip, which you can buy, I think, in any country, and 2 NeuroPixels probes, which are sticked onto each other to be able to attach them to the same micromanipulator to save some space. This is a craniotomy.
Hang on, this is something, there's probably a NeuroPixels 2 probe, right?
No, it's a NeuroPixel 1. It's 2 NeuroPixel 1 probes stick to each other.
Okay, good. So this is something that people can do if they buy. Okay, good.
Yes.
Sorry.
Yeah. You can use dental cement or epoxy, and you can literally stick 2 probes together by eye, trying to be careful to have them very parallel to each other, and you can then attach them with 2 head stages to a single mic rod attached to 1 manipulator, which allows you to more easily insert your probes, because it gets very crowded very quickly. As you can see
good.
Here,
so I apologize. Yesterday, somebody asked this question and I gave them the wrong answer. I told them that this could not be done with NeuroPixels 1. In fact, it can be done with a single manipulator if you glue 2 probes, one to the back of the other. Okay, thanks. To the back to back or back to front? So
the probes are not. So the shank is at the top of parallelepiped like that. So it's literally like that you stick them. So top to top, so that the shank can be closer to each other, because in this direction they would be too far from each other.
Okay, top to top. Okay, great, thanks.
Okay. Yeah, you might break probes doing that, by the way, so be careful. And so the reason why we do this is so that the craniotomy gets less crowded, because as you can see here, you don't really see it well, but this is in a saline bath, and on the side you have a silver wire ball which is going to the ground and the reference, and on the left here you have your LED attached on another manipulator. So if you the more things you can put on single manipulator, the better it is, because craniotomies are small. And so yeah, so steric problems during your experiments are a thing you need to think about when you decide upon what kind of light delivery device you want to use. So the interest of this LED tip is that it's very flexible. It's on another manipulator, so depending on where your first probe is, depending on which brain region you want to hit, you can position it anywhere above your craniotomy, and it's essentially infinitely reusable. It never breaks. One time I even hit it with my hand, and the LED didn't break. So it's really not like a NeuroPixel probe. And importantly, you don't insert anything else but the probe in the brain, so there's no tissue damage in this case. But there are some cons to this technique, which is, first of all, that it's variable across experiments. The illumination of the LED with respect to the probe will be a bit different depending on your mouse. And this can lead to issues, because then the artifact on your probe will not be very consistent, and also you won't be able to maybe stimulate your neurons as well, and you need to think about this. And also, of course, the power quickly decays with depth. It's not red light, it's blue light, so it scatters a lot, and you can only get 1 or 150 micrometers down below the surface before it completely fades away, and you can't make your cells respond anymore. So there's an alternative technique that we've just implemented in the lab, which is to use a tapered fiber inserted in the brain. So optogenetics are selling these. I don't know if any other, I'm not trying to advertise for anyone, I just don't know any other company selling them. What you can do is stick one of these implantable fiber stubs onto your probe and keep them very close to each other, really like the dual probe that I told you about on the other slide. Here you can't really see it, but this is where the probe shank is. And here on top, I've just used dental cement to attach one of these glass fibers, which you can see do not only illuminate the tip, but illuminate on the whole on the length of the fiber. You can see it on this image as well, which allows you to more homogeneously illuminate your neurons along the depth of your recording. So of course, this is the obvious advantage, but another advantage is that a single micromanipulator can hold both together, so it gets less crowded, and you have more consistency in light delivery across recordings because they stick to each other. They will always be at the same distance, and you can be very reproducible in the way you actually stimulate the neurons that you record with your probe. But sadly, they would break with the probe, not like the Thorlab LED. This would, like, if you break your probe, you'd break your LED. But anyway, I guess breaking the probe is worse than breaking the tip itself. So really, I don't think it's a problem. But mainly, there is more tissue damage because you actually stick another piece of glass into the brain, which is not the case when you use optrodes. So this is talking about a bit about the future. There are some NeuroPixels probes with on-site LEDs which are under development. These are examples from other studies. And the main interest of these probes would be that just like the implantable glass fibers, it would allow you to illuminate very deep. You wouldn't have any issues with spatial decay of the light. But also you would be able to be more specific. If you had different shanks with different LEDs, you can decide to only illuminate one part or another. And because the light is shining away from the probe, you might have smaller artifacts. But that's something that we need to, it's not been tested yet. So this is just theory at the moment.
One quick comment is, I mentioned this in the very first lecture, this stuff is under development, but we don't have the funds to bring it to commercialization. So it's basically unlikely that for any project that you're thinking about doing now, you'll get NeuroPixels probes that emit light. So make other plans.
Yeah, I'm just mentioning them as a principle because this would be the dream. This is more about the future than anything you can do right now. The interest is that you wouldn't have any more tissue damage than the one you make with the electrode itself. Okay, so now that you've decided, you've chosen a light delivery technique, what do you do during your experiment? Which protocol do you choose to illuminate your brain? It really depends on your biological application, of course, but I'm going to tell you about optotagging. So first of all, you need to think about power of your simulation. The goal is really to titrate it to the minimum, eliciting spiking, because you don't want to inactivate channel rhodopsin too much. So the minimum is good. And then these are things that Andy already mentioned. So the shape of the stimulus onset, ideally, if you were using a tapered onset, a slow ramping onset, you would be able to get rid of artifacts. But in the case of optotagging, you care a lot about the timing of your neuronal responses. You want them to be very time locked to the stimulus. So we use a square wave to ensure a fast timed response. And then the duration of your stimulus should be long enough to elicit spiking, essentially. And you can make it shorter in order to fit a lot in a recording, but really there's no rule for how long or short it needs to be. Just make sure that you illuminate your brain long enough so that neurons start responding, and that the offset artifact does not overlap with the spiking as well. So if they take 5 milliseconds to spike, you don't want the offset to happen at 5 milliseconds. You want to make it last a bit longer. And then the interstimulus interval between stimuli, you want to wait long enough to allow channel rhodopsin recovery, because as you know, channel rhodopsin, the opsin that you express genetically in your neurons, inactivates with time. The onset current is bigger than the steady state current. And if you compare these two, and channel rhodopsin takes some time, which is counted in seconds to recover. So if you want to get a big response again for your next stimulation, you should wait about 10 to 20 seconds, depending on how you want to do it. Just keep these figures in mind when you design your protocol. And finally, should you use trains or steps? Just also the duration of your stimulus in the interstimulus interval, you want them to be long enough to allow for recovery and to see spiking, but you also want to do a lot of them in each recording. So they should be short enough to be, so that you can have 100 or 1,000 of stimulations per recording. And then you can use trains rather than steps, because then if you use a 10 Hertz train, the first stimulation will elicit a big channel rhodopsin response, and the subsequent one will elicit a small response. And in this case, you know that your response is biological. It's not some artifact being picked by kilosort and being clustered with another neuron or something. An example of which I'm going to show you in a minute. So now let's talk about spike sorting and how to deal with artifacts. This is what we're talking about. So earlier a question was asked about how consistent across channels a light artifact was. Here's an example. It really depends on the recording, but in this case, you see that the artifact does not saturate, and you see that on top channels, it's deeper than on bottom channels. And importantly, you also have a ringing artifacts due to the causal filtering happening on site on the NeuroPixels probes. It's very important to keep that in mind. The artifact is not consistent across channels, which means that common average referencing will not work as well as it could, but we're going to discuss that in a minute. So what kind of problems can it lead to? So first of all, sorry, the physical basics of artifacts. Just a reminder, this is due to the Becquerel effect or photovoltaic effect, where if you shine light on a metal, you will get electrons ripped off and you will get current, which this is a paper where they tried to shine light on metal electrodes and glass electrodes, and they were just to directly compare what happens. And when you use a glass electrode, you have no artifact or a much smaller artifacts in other cases. But it's really related to the light interacting with the metal of your electrode, which silicon probes are made of as well. So you will have artifacts. So what are the issues caused by artifacts? The first one is false positives. Artifacts can be picked up as spikes in some cases. As Andy told you, you can trash them away during spike sorting, but there are cases where it's not as obvious and they remain. And this is what your responsive, what the per stimulus histograms would look like in such cases. On the x-axis, you have time. Each time, the blue dashed line denotes the onset of light stimulations. And you see that the response of your fake neuron here responds almost as much, even though this is a very high, like a 10 Hertz strain delivery. If it were a real neuron, you would expect to see the inactivation of channel rhodopsin, which would lead to a smaller response with time. And if you zoom in on this per stimulus time histogram, you notice that actually the onset of this big response that you see is happening within 1 millisecond. It's extremely time-locked. These are 0.01 millisecond beams. They're way too clustered to be biological, and they happen way too quickly to be triggered by the light. So the timing of your response matters. We're gonna talk about that later. The other issue, apart from false positives, which can be, which can happen, is the inverse, false negatives, where spikes get masked by the artifact. Here is an example of a high spiking neuron at about 100 Hertz. And you see that there is a dip in the onset of its response to the light, which is zoomed in here. And really, there is no reason why the neuron would stop firing suddenly when you start the light, and also why it would happen in the past. This really doesn't make sense, because as you see there, the neuron stopped firing from -4 milliseconds or something. And we're going to focus on this phenomenon now and explain to you why this happens, and like teach you how to notice these things and trash them away, essentially. So here is now again an artifact on a single channel this time, not across channels. You see that it's not saturating, but it can saturate in some cases. It really depends on how far your LED is with respect to your probe, and it comes back to baseline. Now you need to think about what is the data that kilosort is going to see to do its spike sorting, because it's not the data that you see when you're plotting raw data. Kilosort, as Andy reminded and Marius yesterday, is doing some pre-processing to make your data look nice so that it can extract spikes better. So the first thing it does is median subtraction across all channels, assuming that if you have something which is correlated across 300 electrodes, it can only be interferences, right? So you want to subtract that away. This is what people refer to as common average referencing. Then it filters your data. It high-pass filters it by default at 300 Hertz, but you can set this parameter with a Butterworth 3-poles filter, which is done in a causal and anti-causal directions. It passes the filter in both directions. And as I don't know if you know that, but high-pass filtering with a 3-poles filter, when you have very fast deflection like that, leads to ringing artifacts. Because it's passed in both directions, you will have rebounds happening right before and after the artifact after filtering. If you want to read more about it, you can. I advise this reference, which is quite nice. This is due to the fact that the cutoff frequency of any given filter, if you're trying to make the cutoff frequency too steep, you will have a higher gain post-filtering for frequencies very close to the cutoff frequency right after it. Whoops, sorry. And finally, Kilosort is doing whitening. So we're going to talk about it in the next slide. Marius describes it as being spatial filtering. That's essentially what it is. It chooses the 32 closest channel and it decorrelates them. It's also a way, just like median subtraction, but it in a more accurate manner to remove correlated signals across channels. Okay, so now let's find ways to handle this problem. Essentially, what you want to do is subtract the artifact, as Andy said. And you can indeed do a good job with it. So first of all, here is exactly the same the same plot as this one there, but now shown across every channel as a heat map. So red corresponds to high voltage and blue to low voltage. So right after the onset of the artifact, you have a huge dip, and before and after, because this has been high-pass filtered, you see in red big ringing artifacts. And because the artifact is not consistent across channels, the filtering artifacts aren't either. Around here, because the artifact was deeper, the ringing, the rebounds were also bigger in the past and in the future. This is an average of 10 artifacts, by the way, just to make it look more smooth. If you just apply common average referencing, this is what happens. Because the artifact isn't consistent in time across channels, it doesn't work super well. Again, it really depends. Looks like for the imaging artifacts that Andy showed, it worked much better. That's essentially something you need to try for yourself. Just be aware of these pre-processing tricks and apply them to your data and see whether it works or not. In this very particular case, it did not. You still, because the artifact wasn't timed exactly similarly at the top or the bottom, you still have very strong negative deflection or positive deflection depending on where you are on the probe. And it did not get rid of the ringing artifacts, which are stronger here than up there. And so now I'm going to show you what Kilosort sees. Kilosort also whitens the data, as I just said. So it's better now. These big ringing artifacts disappeared, but you still have some stuff in the middle there. This is in general not a problem because they will be found as spikes, which will then be subtracted from the data as template matching iterates. So you can, as Andy said, directly feed your data to Kilosort, but this will lead to the kind of false positives and false negatives that I mentioned earlier. And if because you have so many neurons, you have hundreds of them, you can't always visually inspect all of them, and some of them might you might not find some false positive or false negatives. So it's maybe more safe to try artifact subtraction, which gives you this kind of thing. What you do to get to this point is you average your artifact across all your simulations, which is 1,000 in this recording. And you assume that it's going to be consistent across stimulations, and that if you subtract it from individual trials, you can then remove most of it, taking into account its inconsistency across channels, because the mean will also be inconsistent across channels. And if you do that, and then redo this high-pass filtering, median subtraction, and local whitening, you get to these results. But you still have some stuff there, which usually is very confined to the time right after the onset of the artifact. So you can simply blank it like that. These are 300 microseconds, and it's fine to trash 300 microseconds of data overall. You can replace these by interpolating values between 0 and 300 microseconds, and most of your problems will be gone. If you do that, this is what happens. So this is the false positive example I showed you before. I found that, respike sorted it after removing the artifact, and the artifact was gone. So this is something you might consider, or you might just want to be very careful. But again, this is something which depends on your data sets. You need to look at whether you're having issues or not. And if you're having too many issues to handle them manually, then try to subtract the artifact from your data. Okay, so
Maxime, can you go back one slide?
Yes.
Sorry to interrupt you, but do you do when you do the median subtraction? Do you do it across all channels simultaneously, or do you do it in this demuxed fashion? Do you know what that is?
Yes, global demux. No, no, this is not with global demux, which is not what Kilosort does either, right?
That's correct.
So yeah, so maybe I should mention it then. So you can see here that you have chunks of channels which seem to be correlated with each other, and you have hard transitions between these chunks of channels. And this is due to the fact that on the probe, the channels are not actually acquired simultaneously, they're multiplexed in sub-banks. And this is why Bill Karsh implemented something called Global Demux, which is available in SpikeGLX, and you can run as a Windows application as well, which will do essentially fancy median subtraction, taking into account the difference of timing of these sub-banks of channels being acquired together. I don't know if you mentioned it, it's quite advanced, but I did not try doing it in this case because, you know, median subtraction works well, and I wanted to really show what happens if you do not do anything to your data. But yes, this is a very good point. Okay. So, yeah, so, you know, it solves some problems, but not others. And, you know, essentially, it really falls down to the manual curation. This is the time when you will filter your data with your, you know, neuroscientist experience and make sure that there is no trash in your paper, which you will realize at the reviewing stage, which is usually too late. So, general advice on manual curation, which is not really related to optogenetics, but just more like a general idea. How much time do I have here? So first of all, drift. So there is drift and external interferences, and Kilosort is awesome, but no algorithm is perfect. So really do not trust neurons you haven't visually inspected, even though this might be tempting.
Maxime, you have 5 minutes in total. If you want to also answer a couple questions, you may want to end sooner.
Yeah. So, okay. So I'm skipping over that. You can look at the slides, but essentially look at your data in details. Do not just trust the output of Kilosort. In general, it's great, but it's always better also to get a gut feeling about the data. That's the only time when you will look at your data in detail, because you have so many neurons. Just go in Phi and look at spikes, you know. And the specific caveats of correction of datasets without stimulation is this kind of stuff. So this is a beautiful screenshot of Phi layout. You see in red one neuron and in blue another neuron. Sorry, another cluster of spikes picked up by Kilosort. And it happens, I'm not showing it here, that the waveform templates found by Kilosort were very similar. And if you were not being careful and not looking at the mean waveform, not the model waveform, but the actual average of the raw data, you could merge these neurons together. And this is when you get this kind of artifacts, right? You see that the distance between the blue machine gun-like spikings corresponds exactly to the inter-train interval of your stimulation protocol. So look for these things, and manual curation is important when you have artifacts, because even if you subtract them, you can still find these kind of patterns. And then finally, very quickly, data interpretation. How do you tell that your neuron is responsive or not? So is this neuron responsive? This is a very obvious case, but you know, you don't want to simply be eyeballing cells. You want a principled way to tell whether your beautiful output from Kilosort is responsive to the light or not. So you have a rate threshold, of course. So I don't have time. So these are very trivial things. Just use the baseline, assume Poisson distribution, if you have a p-value lower than a given threshold on several consecutive beams, you tell that your neuron is responsive. But it doesn't mean that it's directly activated by the light, because you can have polysynaptic effects where neurons are connected to other neurons in the circuit and they might be indirectly responsive to the light. So you also want to look at the time of your response. Is your neuron directly responsive? It should be between 1 and 10 milliseconds on average. If it's anything slower, it's a bit dodgy. So this review from Buzaki in this paper are discussing these questions. You can go and look at them if you wish. The fact that a neuron is not alone, it's in a circuit, it's connected to its friends. So you might pick up the friends as being responsive to the light, not the neuron of interest. So really the killer experiment to do is to use a synaptic blocker. Okay, so here's an example where we were shining light and the neuron was inhibited, but it was not depolarization block. Of course, it was just being inhibited by an interneuron, which was in the cerebellar cortex. Once you apply gabazine, in this case, the response disappears. So if you ever want to make strong statements, you need to use synaptic blocker. First, record your neurons halfway through, so do stimulations, halfway through add a blocker, and then do your stimulation protocol again to tell whether your neurons were responsive or not. Okay, so that's it. Sorry for being a bit long. Just want to really thank Nick and Matteo, who have reorganized this course for the 3rd consecutive year, despite the pandemic. Thank you, like really, to Marius, Cyril, and all the people developing the Kilosort N5, because as an experimentalist, you really see these people coming and give talks and explain to you why they make your life so much better for free. So really, thanks to them, and of course, thanks to Dimitar and Michael, who are supervising my PhD in Michael Horser Labs in UCL. Dana Cohen, who's another PI, who's supervising my work. And Tim Harris and the funders, without whom there wouldn't be any Neuropixels probe. So thanks to all.